they say that Stephen Hawking feared most. There's a lot of things that people have said Stephen Hawking feared most, but one thing he didn't fear was this channel. He knew how much we loved him. Anyway, let's take a look at what might be happening inside a black hole right now. Something big just ate a star. It wasn't an animal, more like a dead one. Now, I know that sounds confusing. Let me explain. Stars come in all different masses, from tiny red dwarfs to monsters over 300,000 times the mass of our Sun. But no matter their size, they live fast, die young and go supernova. Well, maybe not so fast. Massive stars burn through their hydrogen fuel in only a few million years, but smaller stars can live for trillions of years. When they exhaust their supply of nuclear fuel, these dying embers collapse in on themselves, igniting the fusion of heavier elements until they produce iron, and when they can no longer sustain even that, they die. A supernova explosion blasts away the outer layers of the star, leaving behind an exposed core, and that core is either a neutron star or a black hole. So when I say something big just ate a star, I mean a giant ball of plasma just got devoured by a black hole. This giant ball of plasma is called the accretion disk. In the final stages of a massive star's life, it blows off its outer layers and forms a glowing cloud of debris around the black hole. Then gravity does what gravity does and pulls that debris inwards. As the material approaches the black hole, it heats up to millions of degrees and emits X-rays and gamma rays that can be detected by telescopes here on Earth. These emissions make the accretion disk visible, despite the fact that black holes themselves cannot be seen. But before we continue, think about what would happen if you fell into a black hole. You probably already know that nothing can escape a black hole, not even light. Once something crosses the surface of a black hole, which is known as the event horizon, there's no turning back. And as you approach the singularity at the center of a black hole, gravity pulls you apart. It's called spaghettification because you become like spaghetti. So you're getting pulled by gravity towards the singularity, but the further you get pulled in, the further apart your feet get, eventually ripping your body to shreds. When an entire star gets devoured, the process happens in reverse. As the star collapses in on itself, it's like pushing down on a giant blob of jelly, squeezing it to make it smaller. But unlike your mum's jelly mold, the star's core doesn't just get squished down to half its original size. Instead, the entire mass gets squeezed together. This means the gravity gets stronger and stronger as the star collapses, and when it becomes strong enough to overcome the outward push of nuclear fusion, gravity wins. Gravity wins all the time. The inner core, which used to be the size of a star, gets compressed to a sphere only a few miles across. That's roughly the size of Manhattan Island. At the same time, the outer layers of the star get blown out into space, forming an expanding shell of debris. Eventually, the debris from this stellar death throes spreads throughout the galaxy like spilled spaghetti sauce. But not all black holes are created equal. Some are born relatively small, while others start out huge. The smallest ones are known as stellar mass black holes. They usually form when a massive star goes supernova and leaves behind a neutron star or black hole remnant. If the remnant has a mass greater than 3 times the mass of our Sun, it's a black hole. Stellar mass black holes are also the most common. NASA believes that there could be as many as 100 billion of them scattered throughout the Milky Way. On the other end of the spectrum, there are supermassive black holes. Unlike their stellar cousins, supermassive black holes aren't born from the remains of dead stars. Instead, they form gradually as smaller black holes merge and grow. Today, they're the largest known black holes in the universe. Their masses range from several thousand to billions of times the mass of our Sun. Our very own supermassive black hole, known as Sagittarius A star, lies at the heart of the Milky Way. A team of astronomers led by astrophysicist Florian Piesker recently captured an image of this beast in action. Taken with the Event Horizon telescope, the image shows a blazing orange ring with tendrils of plasma extending over 6,000 astronomical units from the center of the black hole. To put that distance into perspective, it's roughly the size of the orbit of Pluto. But Sagittarius A star isn't nearly as massive as some of its supermassive siblings. In fact, it's relatively small, weighing in at just over 4 million times the mass of our Sun. That makes it about 1,000 times less massive than the supermassive black hole at the center of the Messier 87 galaxy. And that's the black hole that Piesker and his colleagues previously imaged. It's safe to say that the recent image of M87's black hole was a big deal for astronomers. It provided the first direct visual evidence of the event horizon and the swirling accretion disk around a black hole. It also gave us a better understanding of how matter behaves near a black hole. One of the biggest mysteries surrounding black holes is what happens to objects that cross the event horizon. According to Einstein's theory of general relativity, once something crosses the point of no return, it can never come back. Not only that, but it disappears from the universe forever. However, quantum mechanics suggests that information cannot be destroyed. So what happens to it? One idea is that it's stored in the black hole's event horizon, which would mean that every black hole contains a record of everything that's ever fallen into it. This is Hawking's famous paradox. But what if instead of being destroyed or stored in the event horizon, information is carried along with the object as it crosses the point of no return? This is what a new study claims to show. It's impossible to observe what happens inside a black hole directly, but researchers have been able to simulate the behavior of matter near a black hole using computer models. One such model was developed by a team of physicists at the University of Vienna. They created a simulation of a two-dimensional black hole and watched as various objects approached the point of no return. In one simulation, they sent a pulse of light toward a black hole. As the light approached the event horizon, it began to bend and distort until it disappeared from view. But then something strange happened. After the light crossed the point of no return, it re-emerged on the other side and continued on its way as if nothing had happened. The researchers were shocked by their findings. They had expected the light to be destroyed by the black hole, not to emerge unscathed. This is because they had assumed that the black hole would act like a black hole in our universe, which is a region of space-time where gravity is so strong that not even light can escape its grasp. But their simulation showed that this wasn't the case. Instead, the black hole in their simulation behaved like a wormhole, a theoretical passageway that connects to distant points in space-time. If this is true, it would mean that information is not destroyed when it crosses the event horizon, but is instead transported to another part of the universe. Of course, this is just a simulation, so it's possible that the results don't apply to real black holes. But if they do, it would mean that our understanding of physics needs to be revised. We have a long way to go until we understand black holes completely. But the more we learn, the more we realize just how bizarre and mysterious they are. If you want to support us, you can find us on a crowdfunding platform. Thanks for watching.